I've told you a number of times through this semester that we're going to get a single graphing question on this exam. We will get a single graphing question on this exam. Okay, you will be asked to calculate the slope or to use the y-intercept or one of those things, either the slope or the y-intercept, to find something, to get something. Now, we've done a number of those examples over the semester, including with some of the activities that we've done. When we do activities and use the slope to find something or the y-intercept to find something, we always plot it on Microsoft Excel because it's really, really handy to do that. Excel spits out some nice stats for us, plots a nice graph for us, and so on and so on. Now, you could plot a graph by hand, okay, for your lab activities, but there was no need of that because in the end, when we write our diploma exam, we're not going to have to plot a graph. We will see a graph though. For instance, you may see the graph that you see right here. Okay, that's a reciprocal of image distance versus reciprocal of object distance, kind of like one of the activities that we did actually. 1 over di is a function of 1 over do. We don't have to plot the graph on the diploma exam, but we do have to analyze it. Now, I don't know about you, but I would not look forward to drawing the line of best fit there and calculating the slope by hand. And the reason I wouldn't look forward to that is because, well, what if I'm just off by a little bit? Right? What if my line of best fit isn't perfect? What if it's good but not perfect? I'll tell you this, if you do it by hand, there is a small range of values that they will accept. So you don't have to panic about it if you're doing it by hand, because they will accept a small range of values. But it's not a big range. It's still a fair bit of work to draw that line of best fit and then pick 2 points and do delta y over delta x and so on. So what I'm going to show you today is a quick little method that helps you do basically what Excel did, okay, or at least a Coles Notes version of what Microsoft Excel did. It's not going to plot a graph for you. It's not going to produce this pretty, result that you see on Microsoft Excel, but it is going to give you the slope, and it is going to give you the y-intercept, and it's going to give you the exact value that they expect you to get on the diploma exam. If you flip that little booklet that I handed out a few minutes ago to page 10, then you should see a page that looks like this. Plotting and analyzing graphs from data tables on T83s. You can also do this directly from a graph, not necessarily from a data table. Although if you have a data table, it makes it even a little bit easier. This is ridiculously quick and ridiculously easy. We did not use this as we were doing activities because we wanted the graph, right? We needed to plot the graph, and Excel is the best way to get us that graph. Okay, when we're doing the diploma exam, we don't have Microsoft Excel at our disposal, and we don't need to plot the graph because it's already there for us. What I'd like you to do right now, please, is take out your calculator, and I want you to plot a graph, or at least to plot the data from a graph on the calculator along with me as we follow along these steps. So we're going to go to this graph. That's the graph that you have on the second handout, page 8, that you got a few minutes ago. And we're going to get that data from that graph into our calculators and get the y-intercept as well as the slope from that graph. Okay, here's how we're going to do it. Okay, we take a look at our first data point. Our first data point appears to be right here, okay, and that appears to be at about 0.65, 0.65, and 3.2. Our second data point appears to be at, okay, what is that, 0.678, 0.85, and 3.1. Each of these ones on the y-axis are going up by 2. So 0.85 and 3.1. Our next one, this one's easy. It's 3.0 and 3.0. I like it when they fall right on intersecting points like that. The next one, we've got, what have we got here? 1.15 and 2.6. And finally, the last one, nice intersecting points again. We've got 2.0 and we've got 2.0. So now we've got our data points, okay, as if we have a data table. A little bit of work involved in that. Okay, if we had a data table, it would be even better. Perhaps they will give you a data table on your diploma exam, but don't count on it. Okay, be able to take those data points from the graph. Is everybody okay with this so far? How we obtained that? Yep. Is there a mistake there? Oh, yeah, it is. Sorry, it's 1 and 3. Yes, thank you. That's why I have smart people in this class to point out my inadequacies, my mistakes. Thank you. Yeah, you don't want to do that. You don't want to make it 3.0 and 3.0. Is that good? Does the method make sense for everybody? I mean, we can make a careless mistake like I just made. We hope we don't, obviously. But the main thing today is that you understand exactly how you get that, right? I mean, you've done that since grade 9 or so, right? Just taking points off of a data table like that. Okay, now we want to plug this into our calculator. Now, how are we going to plug it into the calculator? Okay, follow along with me and do it along with me. Hit stat. Okay, this is all in the instructions that I've given you on page 10. Hit stat. Hit edit. So you're going to click on stat, and then you're going to click on the first one. Now, I don't have any data points in there already. Okay, you may, if you've ever plotted a graph, you may have data points in there already. Delete them. It's easy to do it. Just scroll through and click delete. Scroll through, click delete, and so on and so on and so on. Delete an entire table before you start plugging new numbers in. Okay, now I want to start entering these numbers. All my x's and all my y's. My x's, I got 0.65. I've got 0.85. I've got 1. I've got 1.15. And I've got 2. So those are my x's. Make sense? My y's. I've got, what did I say that was? 3.2? 3.2. I've got 3.1. I've got 3.0. I've got 2.6. And I've got 2. Well, there's my data table. You can actually plot this as a graph on your calculator, but there's no need of doing that because you've already got it plotted as a graph on a piece of paper in front of you. Now what I want to do is actually get the slope and the y-intercept from this. So what we're going to do again is hit stat. Stat is the big button here, right? Okay, stat is the button you hit to enter your data table, and then stat is the button you hit to do something with your data table. Hit stat again. This time instead of edit, because we've already got our data table in there, we don't want to edit again. We want to calc. We want to calculate something. Okay, we don't need to edit unless you've made a mistake. We need to calculate. We're going to calculate a linear regression. Okay, so we're going to go to option number 4. Stat, calc, option 4. Hit enter again, and you can see that the equation for this graph in the form of y equals ax plus b, or mx plus b as we like to use, okay, is negative 0.9252, and for the y-intercept, 3.82548. The slope, negative 0.925. The y-intercept, 3.825. Does that make sense? Is that easy? What I'm going to suggest you do is practice this a few times, okay, over the next several days. Okay, practice it a few times. You won't have any trouble if you follow the instructions. You'll get it. Okay, there's no uncertainty to this. It's easy to do. But you do want to practice it so that you're not doing it for the second time on the actual day of the diploma exam, okay? Okay, practice it, a dozen times. Make up a graph. Make up data tables. It doesn't matter what they are. It doesn't matter if it's even good numbers. Just make up numbers and go through this process just to make sure that you're comfortable with doing it. Now, let's actually solve this question. Okay, now that we have the values of a and b, the slope whose value was negative 0.9252, and the y-intercept, whose value is 3.8255. 3.8255. Well, then we can go and actually solve this question. What does it ask us to do? It asks for the slope of the line. Now, there was a typo with this. It shouldn't say negative a decimal b. It should say negative a decimal b times 10 to the negative w. We want the values of a and b. If we take a look at the slope of the line that we got up here with our calculator, what would it be? What would the values of a and b here be here? That's hard to say. What would the values of a and b be here? Connor? 9 and 3, yes. So the first two things we're going to fill in are 9 and 3. I'm not sure, to be honest, what range they would accept on a diploma exam if you're doing this by hand. They would accept a bit of a range. Okay, probably 9 and 2 and probably 9 and 4 would work. Would 9 and 1 work? I'm not sure. Okay, I'm not sure. I'm not sure how far they go. Okay, if you do it on your calculator, you will get the answer that they expect, the exact answer that they expect. So to me, A, it's easier, B, it's quicker, and C, we're guaranteed to getting the exact answer that they have. It's a no-brainer. As far as I'm concerned, it's a no-brainer. Now, this is the tougher part of it. It says, using the y-intercept, the experimental value of the focal length of the lens is what? We did this before, right? We did this exact thing with an activity that we did earlier this year. But let's go through that process again. This is a graph that's a straight line graph. Y is equal to mx plus b. The y-axis is the reciprocal of the image distance. In other words, 1 over di. It's equal to the slope times x-axis, which is the reciprocal of the object distance, 1 over do, plus the y-intercept. Now we got to find an equation from our from our data sheet that matches up with that. The data sheet equation is going to be 1 over f is equal to 1 over do plus 1 over di. Rearrange this to take the same form. It's going to look something like this. 1 over di, rearrange for 1 over di, right? Is equal to 1 over f minus 1 over do. And I'm going to rearrange it even just a little bit more. Okay, it's good here, but I want to make it a little bit better because, look, I've got 1 over di, and then I've got 1 over do. So let's go 1 over di is equal to negative 1 over do plus 1 over f. Now let's start crossing things off that appear in both. 1 over di appears in both. 1 over do appears in both. What are we left with? Slope is equal to negative 1, right? Remember we said that when we did that activity? Slope was equal to negative 1 in this case. What do we find our slope to be? Negative 0.93. Is that within the realm of what we could expect to get? Sure it is. It's really close to negative 1, right? So that's reasonable. What about b, the y-intercept? Its value is 1 over f. So f is equal to 1 over b. The y-intercept here is, we found the y-intercept to be 3.8255. So it's 1 over 3.8255. And when we take the reciprocal of 3.8255, we get 0.26. 0.26, and the units for that would be meters, right? Because the units on the graph are meters. How do we express that? Well, they want the value in what? Not in meters, but in centimeters. So that would be 26 centimeters. What would the answer to this question be? 9326. You will get a graphing question on this exam. There will be one of them. You will need to enter data into your calculator to get the slope and the y-intercept. You will likely need to use the slope for something, and there's a decent chance you need to use the y-intercept, although a slightly smaller chance on the y-intercept than there is for the slope. Okay? Be able to, A, figure out what the slope and the y-intercept are, and B, be able to do what you need to do with them to get what you need. Okay? We didn't want the y-intercept ultimately here. We wanted the focal length. We got it from the y-intercept. Okay? Make sense? There's a few more examples of how you do this in that package that I didn't photocopy for you just because we're not going to have time to do it all today. Download that from my website. On the right-hand side, there's some quick links, and it'll say numerical response practice questions or something like that. Or if you go over to the left side under Physics 30 stuff, you'll scroll through stuff and find the numerical response practice question booklet as well. Okay. The last thing that I want to do with you is tell you about the format of this other numerical response question. Okay, I've told you that you will get one graphing question, and that's 1 out of 50 questions, right? Okay, it's 2%. It's not a huge one, but if you want to do well on the test, then we want to have a fighting chance at all of the questions. And I think we do on the graphing question. Practice it, come and see me, and I think you got a fighting chance on that graphing question. The other one is actually a group of 2 questions. It's a pair of questions. Okay, let's say it's question number 4 and 5. Numerical response number 4 and numerical response 5. It could be numerical response 1 and 2. It could be numerical response 8 and 9, or whatever the case may be. Doesn't matter. Doesn't matter. It's a pair of questions. The first question is going to be a relatively standard question. It may be a little bit more challenging than the average question. It may not be. It may be a little bit longer in terms of how long it takes you to do it than the average question. Okay? It may not be. On average, they tend to be a little bit more challenging, and they tend to be a little bit longer. Okay? But I've also seen fairly short, fairly quick, fairly easy questions in this group of 2 as well. Okay, the first one isn't our concern here right now because we solve that the same way as we solve any other numeric response question. It just might take us 3 minutes instead of 2 minutes, or whatever the case may be. The second one doesn't concern me either, but it is the one that I want to draw your attention to today. The first one will say, solve for this, as you would in any other numeric response question. The second one will say, what physics principles did you use to solve for that in the previous question? Now, how do you fill that in as a numeric response question? What physics principles do you use? Let's say I use conservation of energy. Well, how do I fill that in a numeric response? I want everybody to open up your data booklets right now. Okay, go to your data booklet right now. And I want you to look in the bottom left-hand corner of your data booklet. When you do, you should see something like this that says physics principles. They're numbered, 0 through 9. They used to be numbered 1 through 10. I liked it when they were numbered 1 through 10. You know why? Because there's always going to be 2 physics principles that you'll use. There's always going to be 2 that you're going to list. When we listed these as numeric response, let's say you use physics principle uniform motion and conservation of momentum, you would list in your numeric response boxes 0 and 4, or 4 and 0. It doesn't really matter which order. They tell you it matters what order to put it in, but it doesn't. Okay, in the information bulletin, they've said you can put them in either order, 0, 4 or 4, 0. Okay, so don't worry about that. Let's say we use principle 1 and principle 9. Okay, we fill them in like this, or it could be 9, 1 instead of 1 and 9. The first year they put this type of numeric response question on the exam, they kind of made a mistake. It wasn't really a mistake, but it gave people a bit of an edge sometimes. They were numbered principles 1 through 10. They told you that you had to list 2 principles. And then they said fill in your 2-digit answer or fill in your 3-digit answer. But if they said fill in a 3-digit answer, then they told you that you used principle number 10, right? Because that was the only way you could get a 3-digit answer. So now they've changed it to principles 0 through 9, so you don't get that break. Okay? But on the other hand, you used to have to put them in the right order. Now you can put them in whatever order you want. Okay, so kind of a trade-off. Let's take a quick look at these concepts, and then let's do an example that illustrates how we're actually going to put these into play in a real question. Uniform motion, what does that mean? I think that's pretty straightforward, actually. Uniform motion is constant velocity. So if the net force is 0 in the problem that you're dealing with, then it's uniform motion. If it's a constant velocity, if you've used the equation v equals d over t, any of that stuff, it's uniform motion. Accelerated motion, F net is not equal to 0. In other words, F is equal to m times a, or any of the other acceleration equations. Bottom line is this: if it accelerates, you've used principle number 1. Uniform circular motion. Object is going in a circle. Typically, that manifests itself when you're using F is equal to mv squared over r, which, remember, doesn't actually appear on our data sheet. We have a is equal to F over m, and we have a is equal to v squared over r. When we combine those two, we get mv squared over r. So just remember that. Okay, if you use that equation, mv squared over r, then you've used uniform circular motion. The work energy theorem If you've used the idea that work is equal to the change in energy, then that's the work energy theorem. Conservation of momentum, well, I think you know what that is. PI equals PF. Conservation of energy, EI equals EF. Conservation of mass energy, somebody can tell me this one. If I'm using conservation of mass energy, which equation have I used, Riley? Right, E equals mc squared. Conservation of charge, it's not really a math thing with an equation, right? If you use the idea that charge has to stay the same, that's conservation of charge. Okay, that might be a situation where you're balancing the number of protons, right? The atomic number between one side and the other in a nuclear reaction. Okay? If you're balancing the top number, then that would be nucleons, conservation of nucleons, balancing the number of protons and neutrons. In wave-particle duality, the idea that sometimes light behaves like a wave, sometimes it behaves like a particle, sometimes electrons behave like waves, sometimes they behave like particles. By and large, you'll use principles 0 through 6. Okay? It's not out of the question that you could use 7 through 9. I have seen it used before. Okay, but usually it's 0 through 6 because usually these problems involve purely mathematics. Okay, and they're the ones that you're going to do the math for. Okay, we understand all of these things, right? It's just a matter of knowing these are the principles. They're listed on our data sheet, so we don't have to remember, okay, which one's principle 3 and which one's principle 7 and so on and so on and so on. I got a little note at the bottom here. It says sometimes there will be more than one valid way to solve a question using different principles. Don't panic about that. Okay? These are smart people that write this exam. Okay? They know different ways of solving things. They've had 50 people go over that question probably. Okay? They've had a dozen people do different solutions to this problem. They know every possible way of doing this problem. Okay? If you do it a certain way, if it's a valid way, okay, if you do it a certain valid way, and you say principle 0 and 2, and somebody else said it was 2 and whatever, and those are both valid ways to do it, then that's okay. Does that make sense? Sometimes you may use 3 or 4 principles. Pick 2 of them. Again, the answer will be keyed to accept. The computer would be keyed to accept any of those possibilities. Let's say you use 1, 2, and 3. You could write 1 and 2, you could write 1 and 3, you could write 2 and 3, and all 3 of those would be marked correct. So don't worry about any of that stuff. Okay? Just do the question, and then just fill in. The next one's easy, right? Okay. Once you do the question, this part is actually really, really easy. I like these questions, actually, because there's a lot of times where we can get value for this without really having much of a clue as to what we're doing for the previous question. Okay, for example, let's take a look at this question right here. This is the one that appears on page 11 of that booklet that I gave to you. This is already podcasted from last year, as is the next question podcasted from last year. If you download the booklet, then you can see a number of other examples of this, some pretty challenging ones actually. I've purposely put some challenging ones in there, not the easier of the group, but I've put the tougher ones of the group in there, okay? More challenging than probably you would see on a diploma exam. The solutions for those ones are already in the booklet. Okay, so try them and then look back at the solutions and come and see if you need some help. Let's do this one though. Let's do this one just as an example, okay, to illustrate what kind of question you could expect to see. Okay, this might be average or slightly harder than average, but not one of the really, really difficult ones that we could see. But also I've seen easier than this as well, quite a bit easier than this as well. It says the electrons are excited from rest by an electric potential difference of 3.0 times 10 to the 2 volts. You know what I saw? As soon as I read that first sentence, electrons are accelerated from rest. Anybody else notice that? Electrons are accelerated from rest. As soon as I see that, something comes to my mind. 3 words. Yes? Yeah? What are the 3 words? VI equals 0, sure, as a given. But remember what we said yesterday in the last couple of days? Don't get too narrowly focused. Don't get tunnel vision on just numbers, right? Okay, so Raul, you're absolutely right. VI is equal to 0, but don't just get the tunnel vision on, okay, I got a given. I've got a given given to me. Okay, I got a number. Okay, the bigger thing here is that when a charged particle accelerates, we use conservation of energy, which is what you were saying, Shelby, right? The car going down the hill, right? Okay, so we use EI is equal to EF for this. Now, whether we're actually going to use that in the problem or not, we're not sure until we actually go to do it. Electric potential difference of 3.0 times 10 to the 2 volts. Okay, Riley, I'm not abandoning circling my givens by any stretch of the imagination. Okay, that's an important thing. But if you see a concept that jumps out at you, okay, then write down that concept, because that's bigger. That's more important than your givens. Givens are important, but concepts are more important. I mean, you might not notice that as you're reading through it, and that's okay, but try to notice those things. These electrons enter a region that contain mutually perpendicular electric and magnetic fields. The electric field has a magnitude of 8.5 times 10 to the 5, and the magnetic field has a magnitude of 2.0 times 10 to the negative 1. Okay, that's about all the notes that I think that I can make there. Maybe I want to draw the electric field. The electric field is down the page. Maybe I want to even go so far, since I'm having the thought, hey, as I have thoughts, I should write them down, right? Maybe I want to even go so far as to say, look, this is an electron, a negative particle that will experience an electric force opposite to the field, and if we use the hand rule for deflection, thumb, fingers, palm, a magnetic force that's acting downwards. I don't know if that's going to help me, but it's thoughts that I had. So as I have them, I like to write them down. We're looking at question 263. By the way, I promise you in that booklet that I've posted online, there's not 263 questions in it. Okay, these come from a few different sources, and the numbering systems that they use in these different sources are different, and I just didn't change them. So 263, whatever it's numbered, it doesn't matter. The magnitude of the acceleration experienced by the electron as it first enters the region. In other words, where I have it drawn there, I've just kind of gotten lucky with where I have it drawn. At that point where I have it drawn, what's the acceleration? Well, how are we going to do that? How are we going to find that acceleration? Anyone? Riley? Good. You know what it reminds me of a little bit? Is the oil drop experiment. A little bit. It's not the oil drop experiment because in the oil drop experiment, we didn't have a magnetic field. Right? In that one, we just balanced, if it was suspended, we balanced the electric force with the gravitational force. Or if it was accelerating, we added them together. Well, here clearly we know it's accelerating because they're asking me for the acceleration. So we're going to add them together here. M times A is equal to QE plus QVB. Mass is the mass of the electron. We're looking for A. Q is 1.6 times 10 to the minus 19. The electric field strength is 8.5 times 10 to the 5. So far, so good, right? That's going to be a positive value because we've already drawn the electric force upwards. If you hadn't drawn it when I did, that's okay. But you should draw it before you go and do this. Now let's add to that the magnetic force, QVB. 1.6 times 10 to the minus 19 is Q. Oh, what's V? How fast is this electron moving as it enters this electric and magnetic field? We don't know, do we? Does anybody have a suggestion as to how I might find the speed that it's moving as it enters the magnetic field? Connor? That's where we're going to use that conservation of energy that we kind of forgot about, right? Okay, we kind of started doing this, and then we kind of forgot about the EI equals EF thing, but okay, we wrote it down when we saw that, so kind of brings us back to that, EI equals EF. It starts at rest right here and accelerates through this potential difference. And then once it gets going that speed, it enters the electric field and the magnetic field at that speed. Starts off with potential energy, it ends off with kinetic energy. Okay, we know what Q is. It's 1.6 times 10 to the minus 19. The potential difference is given to me as 300 volts. Let's solve for V there. Okay, let's solve for V. And let's do this on our calculator here, okay? Let's say 1.6 times 10 to the minus 19 times 300. We're going to multiply that by 2 to get the half over. We're going to divide that by 9.11 times 10 to the minus 31. And then we're going to square root that. And we're going to get 1.0265 times 10 to the 7 meters per second. Let's plug that in over here now. 1.0265 times 10 to the 7 meters per second times the magnetic field strength, which is 2 times 10 to the negative 1. Now, we're going to make that a negative value because we have the magnetic force drawn downwards. You're going to calculate the value of the acceleration there. Now, I don't remember what it works out to be, but I do remember that it's not a 10 to the negative CD. That's another typo. It's a 10 to the positive CD. Okay, if anybody gets 10 to the positive 11 or something like that, I don't know what it is, but it's a 10 to the positive something. Okay. That's your answer to 263. Now, is that a hard question? I think it's a challenging question. Yeah, I think it is. I think it is a hard question. I don't think it's impossible. I don't think it's an impossible question at all, but I think it's a real challenging question for sure. Okay, if you struggle with this question, don't panic. You've lost 2%, but 2% is not the end of the world. It doesn't mean you're going to get the next question wrong. The next question says, what are the two physics principles you used? It tells you to put them in order, but we're not going to worry about that. What are the two physics principles I used? Well, let's go back. Okay, let's go back to that list. Did I use uniform motion? In other words, is this thing going at a constant speed? No. No, it's not. So I didn't use principle 0. Did I use accelerated motion? Is it accelerating? Yes. Caitlin's nodding her head there, yes. So I used principle number 1, right? Uniform circular motion? No. First of all, it's not even going in a circle. That may look like a circle, but when you've got an electric and a magnetic field, it's not a circle. Okay? But second of all, even if it was a circle, I didn't do anything with the circle. Right? I didn't use F is equal to mv squared over r, so I wouldn't list that. The work energy theorem, no. Conservation of momentum, no. Conservation of energy? Yes, EI equals EF, right? Principle number 5. So I would fill in number 264 as either 1,5 or 5,1. Does that make sense? Now here's why I like this question. Even though 263 is, I think, a pretty challenging question. 264, let's assume for a second that once we read through this and circled all those things that we circled in that paragraph, we didn't really know where to go with it. We were at a loss. It's just like, oh man, I can't get this. We can still get 264 right. Because we know, even if we don't know how to do the question, we know that it involves acceleration, principle number 1. And we know, because the electrons are accelerated from rest to a certain speed, that it involves conservation of energy. So we know what the concepts are, the principles. It's 1 and 5, or 5 and 1. We don't have to be able to actually do the question to get 264 correct. Okay, so don't give up on that. If you see that question, sometimes you get a nice easy one. If you do, that's fantastic. If you don't, and you're struggling, and you're not sure how to get it, okay, just take a step back from it and say, well, look, it looks like this concept and this concept would work. I have no idea how to apply them, but it looks like if I did, then I could get the right answer. Pencil them in, and at least get the second question correct. Okay. I would go so far as to say 95% of us, 95% of you could have got 264 correct if you gave it some thought, even without getting 263 correct. So don't give up on it, okay? Even if you have trouble with 263. Does that make sense? You guys okay with that format of numeric response question? Okay, so today was numeric response day. The first one that we're going to see, that we know we're going to see, is the graphing one, right? not necessarily the first question, but you know what I mean, the first different type of numeric response question. And then the second different type of numeric response question is this, like 263 and 264. In that booklet that you can download, there's more examples of both. Some challenging examples of this type of thing. Some more challenging examples than you're likely to see on your diploma exam. So don't panic if you struggle a little bit, okay? Come and see me, we'll get the solutions, do what you can.